Okay, let's look at the first problem. This is a problem that used to be in your textbook, but I don't think it is there anymore. Anyway, this is a problem related to your normal tangential coordinate system. So the problem goes like this. There is a stretch of road where this car enters, and it is currently at this point. So this is a car, and there are a few points on this road. Okay, so we're looking down at the road from top. So this is point C, this is point B, sorry, and this is point A. Okay, so the distance between A and B is 200 meters. And the car actually make a turn of 30 degrees as it goes from B to C. Okay, so you can imagine that the turn, this angle is 30 degrees. The radius of curvature at C rho is equals to 250 meters. Okay, so let me just copy down the problem. So problem 1. Okay. Use another marker for that. So when the car reaches point A, it has a speed of 25 meters per second. Okay, so the car is actually going in this direction as it reaches point A, and the velocity is 25 meters per second. If the brakes are applied, its speed is reduced by a deceleration. Okay, so AT is equals to 0.001 s minus 1 meter per second squared. Okay, so this is tangential acceleration. Determine, okay, so determine the magnitude of the acceleration of the car just before it reaches point C. Okay, the acceleration of the car at point C. So this refers to total acceleration. Okay? Okay, whenever you see the word acceleration, usually it means total acceleration, and you should immediately have in your mind this equation. So A is equals to AT squared plus AN squared. Right? Okay, so let's think about how do we solve this problem. So you have a car entering point A at a velocity of 25 meters per second, and now you start to apply brake at point A. The moment it reaches point B or point C, it has an acceleration represented by this equation, where S represents the displacement, right, from point A. So determine what is the total acceleration at point C. Okay. All right. So the acceleration at point C, of course, we know that this represents the acceleration at point C. So we can quickly evaluate the acceleration at point C. So using initial condition, V equals to 25 meters per second at t equals to 0 second. Okay, we can calculate an expression in V, right? The velocity in V. The reason why we would calculate an expression for velocity in V, velocity V, is so that we can actually know what is the velocity at C, which will allow us to calculate AN, right? Because as you remember, AN is equals to V squared over rho. Okay. So V, we start from V dV is equals to A ds, right? As usual, because A is in terms of 0.01 s minus 1. Okay, we'll go to this integration. So v dv, right? So v go from 25, right? You start from 25, and you go to some velocity, right? And v dv. And a, as we know, is 0.01 s minus 1, okay? And this is ds. And this is going from 0 to some displacement downstream, right? 0 to s. Okay? So you have v squared over 2, 25 to v is equals to, so this is 0.0005 s squared minus s 0 to s. Okay? So if you simplify, you get an expression equals to v is equals to 0.001 s squared minus 2s plus 625, and the whole thing is square root. Okay? So this is the expression for velocity at any displacement downstream from point A. Right? Starting from point A, we start to count the displacement starting from point A. Okay? So let's erase this part. Okay. So exactly what is S at point C? Right, we know from A to B it is 200 meters, right? But we don't really know what is this little displacement. We do need to know that because once we know the total displacement from A to C, what we will do is we'll plug S into this equation, and that allows us to calculate the velocity at point C, which subsequently allows us to calculate the acceleration, or the normal acceleration at point C. Okay? So when the car is at C, right, as C is equals to, first 200, right, plus 250, which is the radius, right, multiplied by this angle, this little angle here. And it turns out that this angle is actually equal to this angle, which is 30 degrees. Right, because it's part of the trigonometry. So this angle is also 30 degrees. And as you remember, 30 is equals to what? Right? Pi over 180 multiplied by 30. And so it's pi over 6. And what you get here is 330.90 meters. So that's the displacement from A to C. So with that, we can calculate velocity at point C. Okay? So velocity at point C is basically 0.001, okay, 330.90 squared minus 330.90 plus 625, and the whole thing to the power of half. Okay? And that gives you 8.526 meter per second. So that's the velocity at point C. With that, we can calculate A of n at point C. Right? So that's equal to VC squared over rho at C. Okay? So that becomes 8.526 squared divided by 250 meters. And what you get here is 0.2908 meter per second squared. So that's your A and C, right? The normal acceleration at point C. What about the tangential acceleration at point C? The tangential acceleration at point C, AT, is given by basically V dot, right? So you differentiate velocity, which we have an expression for, one more time with respect to time. And what you get is 0.001 330.9, okay, minus 1. Okay, this is actually given to you, right? As you remember, this was AT is equals to 0.001 s minus 1. Right? Actually, it was given to you. And what you have here is minus 0.6691 meter per second squared. So now just do the vector sum of these two, and you're going to get A, total acceleration, equals to 0.2908 squared plus minus 0.6691 square root, and the result is 0.730 meter per second squared. So that's the total acceleration at point C.